Hello everyone. So today we are going to solve the problem Neelu's walk in the park. And the problem statement states that Neelu and Miss X are uh, taking walk together in a park, and they came across a long queue of people standing in front of. Okay, so Neelu has given a task to Miss X uh, that has given a task to Miss X. Okay, so the scene is that every person can look at people ahead and behind them in a queue, but there is a catch. A person cannot look beyond another person whose height is strictly greater than him or her. Okay, now Neelu wants Miss X to find out for each person in the queue that out of all the people he can see in front of him or her, he find out the minimum and do the same for the all the person behind him or her. Okay, and then give the absolute difference between the heights of both the person. That is, suppose if there are n persons and they have height h1, h2, h3 and so on till hn. So for person with height hi can see up till person height hl such that hl is the first person left of hi such that hl is greater than hi. Also, it can see up till HR on the right side of him or her, such that HR is the first person whose height is strictly greater than the ith person. Now, for these persons, what Miss X has to do is among these persons from HL to HI minus 1 and from HI plus 1 to HR, she needs to find the minimum height. Suppose the minimum height among these peoples are HA and the minimum height among these peoples is HB, then the answer to this problem will be absolute value of HA minus HB. Okay, this will be our answer. So the as a constraint says that there can be 2 into 10 raised to power 5 person. Okay, so as there can be 2 into 10 raised to power 5 persons, the value of n can be equal to this much, and we know that in a best scenario in the given time, which is 3 seconds, the best complexity or the worst complexity on which we can work is O of n log n. We need to find our solution in O of n log n. Okay. Now, what we can do is let's break down the problem in two parts. Okay. First, for every hi, we need to find hl and hr. Okay. The first part is for every hi, we need to find hl and hr. Okay, now in the given range we need to find the minimum element. Okay, so for the second part is for range L to R, we need to find minimum element in this range. Okay, so now these both have became a very standard problem. This is a very standard problem based on stack, and this is a very standard problem based on segment tree. It can be more efficiently done using sparse matrix, but as this was a contest based on trees, we'll use segment trees. So how we can calculate HL and HR? Okay, so we'll use stack for it. Let's take the example which was given in the question. that is 25, 2, 7, 10, 4 and 18. Here what we'll do is we'll start iterating from the left. Okay, um, what I did was I started it from first index, had one extra index on the right and one extra index on the left with the height 0 respectively. Okay, we'll see later why we are doing it. Now what we'll do is we'll have a stack here which will be currently empty. We'll do three operations. Okay, suppose if the stack is empty. Okay, suppose if the stack is empty, what will what we will say that here I can see everyone. Okay, and if stack is not empty, if stack is not empty, we'll pop it, we'll pop it until the top is less than or equals I. The top element is less than or equal to hi. Else we'll say after this is done, if the top element is greater than hi, we'll say that I can see up till top element. Let's see how. So we'll start from here. Okay, so initially the stack is empty, that means 25 can see everyone in front of him. In front I means to the left of him or her. Okay, so we'll say that 25 can see up till 1. Okay, so we'll say 25 can see up till the first index. Okay, now we'll insert 25 in the stack. We got 2. Okay, we got 2, the height is 2. We'll see that okay, the height stack is neither empty, neither the top element, the height of top person is less than the current height. So we'll say that I can see up till the top element which is at index 1. So I can say, we'll say that the person at index 2 can see up till the person at index 1. Similar, and then we'll insert it in the stack. Now we got 7, height as 7. Stack is not empty, but the top element is less than current height. So we will pop it. Now we'll see that again, is 7 greater than 25? No. So we will say that now 7 can see up till the top element of the stack, which is 1, and then we'll insert 7 into the stack. Similarly for 10, 7 will be less than 10, we'll just remove it here. And then see that 25 is greater than 10. That means 25 can see up till, 10 can see up till 25, which is at index 1. So that means the fourth person can see up till the first person. Now we will insert it into the stack. Now we come at index 5. His height is 4, which is less than the top element of the stack. Okay, that means this person can see up till the top person in the stack, which is at index 4. So we can say that this person can see up till index 4 only and can't see the person beyond him or her. Similarly for 18, 10 will be less than 18, so it will be removed from the stack. 25 will be greater than 18, that means 18 can see up till 25, which is at index 1. We'll do it now. We know the next greater element to the left for each element. Okay, this is the next greater element to the left of everyone. Okay, 2 can see up till 1, 5 can see up till fourth person only, not beyond him or her. Okay, similarly we will do it for next greater right also. Next greater element up till right. We will clear the stack. We will start again. 18 can see up till him. Okay, 18 is pushed back. 4 is less than 18, that means 4 can see up till 18 only, okay, and 4 will be pushed into the stack. 10 is greater than 4, 4 will be popped out. 18 is greater than 10, so 10 can see up till 18 only. 7 is less than 10, so 7 can see up till 10 only. 2 is less than 7, so 2 can see up till 7 only. Similarly, 25 is greater than 2, 2 will be popped. 25 is greater than 7, 10, 18, everyone. So if stack is empty, we will assign it the last person, which is 6. Now, why we had this 0, these indices, okay? So we are assigning the next greater left and right in terms of indices only. So we can see that in the question it is said that for a person at the end of the queue in the direction there are no person, the shortest height can be taken as 0. That means for the person on the left end, the next greater left's height should be 0. Okay, so we will then assign it at index 0 instead of index 1. The next person to him will be index 0. Similarly, for him will assign index 7. The next greater right for the rightmost element will be 0. Okay, now we have calculated next greater left and right very efficiently. Now our other problem is to find the minimum in the range L to R. That we can do using segment tree. Okay, so suppose we have a segment tree. We need to create a segment tree for an array of size 3. Okay, suppose it is 2, 1, 7. So first, as we discussed in the class, we will need to have the size of this array in power of 2. So the nearest power of 2 is 4. We will insert an identity element here such that this element is identity in terms of minim. That means if this element is I, so the minimum of any integer a with I will return a. Okay, that means our I must be infinity. In the question, we have been given that the largest element, the largest highest height one person can have is 1e9. Okay, that is 10 raised to power 9. So we can assign I any number which is greater than 1e9. Okay, I can be 1e9 plus 1, 10 raised to power 11, and for simplicity's sake I'll assign I as 1e16. Okay, that is 10 raised to power 16. Now we have infinity here. Now how we are going to store it in our system, in our program? We'll use an array for it. How? So we have array 2, 1, 7 and infinity. What we will do is we will create another array of size 2 into this array. Suppose n is now 4 here, we will create an array of size 2n. Here every index will denote a node in the tree. So for ith node, its left child will be 2i and right child will be 2i plus 1 if it is 1 based. Okay, and the left child for ith node, its left child will be 2i plus 1 and right child will be 2i plus 2 if it is 0 based. What I mean is, suppose if we start from 0 base, the root will be 0, its left child will be 2 into 0 plus 1, right child will be 2 into 0 plus 2. Similarly 3, 4, 5, 6. Okay. For 1, its left child will be 2, right will be 3, and similarly 4, 5, 6, 7. We are going through this approach. Now what we will do is, first of all the leaf nodes of the segment tree, suppose there are n leaf nodes, will be the last n indices of this array. Okay, this will be root, this will be root's left child, this will be root's right child, this will be second node's left child, right child, this will be third node's left child and third node's right child here. Now first, its index is first 2, 3, 4, 5, 6, 7. Now we want its leaf nodes to have the values that we have in the array. So what we will do is, we'll map these values from here to here. We'll say that tree of I plus n is equal to array at I. So we'll have 2, 1, 7 and infinity here. We got 2, 1, 7 and infinity here. Now we'll traverse from lower nodes and eventually go up till the root node to find their value. Okay, the value of these nodes will be the minimum among the both childs of these nodes. Okay, so the value of 3 will be minimum of the values at indices 6 and 7. Okay, this is infinity, that will be 7. Okay, we filled here 7 here. Similarly 2 will be minimum of its children from, that is 4 and 5. Okay, so at index 4 we got 2 and 5 we got 1, and for the root node it will be minimum among these two indices, that will be 1. So here we created our segment tree. Okay, let's first implement this part, this much. Okay, so what we had to do first was take input, that is n, then create a vector of size n plus 2. We needed 2 extra indices. Then we'll take input from 1 up till n. Now what we'll do is, we'll create another vectors which will store the next greater element to the left and the next greater element to the right. Then we'll create a stack to help us with our implementation. We name it S. Now what we'll do is, we'll iterate from left to right. Okay, what we did was, we iterated from left to right and followed these set of rules. Okay, so what we did was, till the time, like while our top element was less than or equal to current element, we kept on popping that element out. We kept on removing that element. In this scenario, there can be a case where the stack is already empty. So we'll have to handle it. After that, there can be case that if stack is empty, that means there is no element greater than this element in front of him or her. So we'll say that it can see all the elements. Okay, it can see up to the first element. Okay, and let's make it single liner. Okay. Now if the stack is not empty, that means the current person can see up till the person who is currently at the top of this stack. So we'll say ngl I is the top of the stack, the index set, and then we'll simply push it. We'll simply push the current element in the stack. Now for the right for the next greater element to the right, we'll do the same thing. We'll iterate in opposite direction. Then here we'll just replace the next greater left with next greater right. Okay. Yeah, and we need to ensure that here our stack is empty. And if the stack is empty in this case, he can see up till the last person. That is, he can see up till the nth person. Okay. Now our next greater left and next greater right is ready, except for the fact that the last person, the next greater left for the first person will be 0, and next greater right for the last person will be n plus 1. Now after this much, we had to create the segment tree. Here we'll work for the segment tree. Now I'll make everything public, and first we'll need a constructor to construct the segment tree. Here we'll have the constructor which will take the vector for which we are making the segment tree. We'll store the size of the segment tree here, and also another vector which will store the tree. Okay. First we'll find the size of this vector, and we want it to be the nearest power of 2. So first we'll find k such that k is nearest power of 2 greater than n, and then until and unless our vector is of size equals k, we'll just insert that identity element which we decided, and that was 1e16. Okay. Now once it is created, we'll resize the tree vector here. Then first we'll assign the values of root elements, that was mapped with I plus 1. Now we will assign the values of every other node, and we will iterate from bottom up, from leaf nearest to leaf up till the root. Okay. I will say tree of I is equals tree of min of tree of 2 into I and tree of 2 into I plus 1. Okay. Now our tree is constructed, and how we will perform the query. Okay. So in the class we discussed how to implement the segment tree recursively. Here we will do it iteratively. Okay. Now how to perform queries. Okay. So suppose we have tree. This is our tree. Okay. The index for which they'll store the value will be here 0, 1, 2, 3, 4, 5, 6, 7, 8, sorry, 2, 1, 2, 2, 3, 4 to 5, 6 to 7. It will store for 0 to 3, 4 to 7, and it will store for all the index from 0 to 7. And now the indices of these nodes will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, for an array of size n, the for an array of size n, the value of index I of array will be stored at leaf node with index I plus 1, I plus n. Okay, that is for 0 it is 8, for 1 it is 9, for 2 it is 10, for 3 it is 11, and so on. For 7 it is 15. Okay, so what we will do here, is suppose we have been given a query from L to R. First of all, we will add plus n to both of them. Okay, so that our L and R, suppose if we have been given query for 1 to 7, our L will point here 1 plus 8 9, and our R will point here 7 plus 8 15. Okay, now what we will do is we'll see that okay, up till the point L and R are not pointing, or are pointing up till same node, or L is less than or equal to R, we will see if L is pointing to the left child or right child. Okay, suppose if L is pointing to the right child of the current node, okay, we need to take this value and move L here. Okay, similarly for the right one, if R was pointing here, we would take the value of this node and moved here. But now if R is pointing at the right child, what we will do is we will move to the its own parent. Okay, so how can we see that it is pointing to the left child or right child? So it can be observed that every left child is an even number. Okay, every left child is an even number and every right child is an odd number. Okay, suppose I was the node, so its left child was I into 2, that means I into 2 is even number, and right child was I into 2 plus 1, that means it is odd number. Okay, so if L is even, we need to take the current node's value and move to the other subtree. We need to jump here. Okay, how can we do that? That is a problem. So suppose if L is odd, then we need to move to the next subtree. Okay, so what we will do is, how can we do that is, see from here you can see that if you want to go to the parent node, if you are at node I or j, such that I and j both are children of p, so irrespective of whether you are at I or j, you can go to p simply by dividing I by 2, the floor division. Okay, this one will be ignored during the floor division, that is we will get I plus 0.5. Okay, suppose we got I into 2. If we divide it by 2, we will simply get I. But if we have I into 2 plus 1, we will have I into 2 by 2 plus 1 by 2. That will be I plus 0.5. This 0.5 will be ignored in floor division. Okay, so we'll directly jump to the parent if we divide the current node's index by 2. So if L is an odd number, we divide its index by 2, we jump to its parent. But before dividing its index by 2, if we add plus 1 to it, that is, if we find the value of this thing, this equation, we will jump to this parent. Okay, and same way for R, if R is here and we want to jump here, okay, if we want to jump here, we can simply find r minus 1 by 2. This is how we'll jump. Okay, suppose let's write in the case where we got our range at as 1 and 7. Suppose we have the tree like this again, and this is our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got L equals 1 and R equals 7. So first we added plus n to both of them. We got 9 and 15. So L is pointing here and R is pointing here. So now we will take the value of index I for L and jump here. Okay. For R, we won't take the value of 15 because we need the value of both of these. So we'll directly jump here. Okay. Now, because we need the elements in these range, that's why. So now we want only this node from this subtree. We took it and jump here. For R, we needed the value of this both the nodes, so we went to directly to its parent. Now the value of L is 5 and R is 7. Okay, it was 9 plus 1 by 2, we got 5. It was 15 by 2, we got 7. Now again it is right child, so we will take this value and jump here. L will jump here. Again it is right child, so we won't take it this value and jump here. Now again L is the right child, so we will take its value and try to jump to its right subtree. And L and again it is a right child, so R will think that okay, we need this node also, so it will jump directly to its parent. Okay, so after 3, L will become 3 plus 1 by 2, that will be 2, and R will become 3 by 2, that will be 1. And at the time when L will be greater than R, we will say that all the nodes that we wanted, we have them. Okay, so we stored the value of this node, this node, and this node in our answer. Okay, so storing the values of these node, we stored the minimum among 9. This node gave the minimum among 10 and 11, and this node gave the minimum among 12 to 15. And in this way we did our query. Let's take one more example. Suppose our tree is same. Okay, its index is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Suppose now we wanted to query from this index from here, okay, up till from here to here. Okay, now what would have happened? L was the right child, so it will take this value and jump here. R was the left child, so it will take this value and jump here. Now L was the right child, so it would take this value and jump here. Okay, and again R was the right child, so it wouldn't take this value and jump here. Now again L is greater than R, so our program would have stopped. L would have taken the value of this 9 and this 5, and R would have taken the minimum of 12. So in this scenario also, we took the minimum of all the elements in the range 9 to 12. Okay, and since they are traversing upwards, again the time complexity is O of log n, since the height of the tree is log n. Okay, so this is how we are doing our query. So let's write the program for this query. Over here we are writing the program for query. Suppose we want, first we'll add n to both L and R. Now we will have our result as that identity value 1e, that is 1e16. Now we'll iterate by, while L is greater than or less than or equals to R. Once L will be greater than R, we'll stop. Now we need to check whether L is the left child or the right child. So if L is an odd number, it is the right child. So if L is odd number, how we can see? We can check it like this. If L is right child, we will consider the current node. Sorry. And now we want L to jump to the next node. We want L to jump to the next node. So we want L to be, we want L plus plus, okay, and then we want, or we can say it like L equals L plus 1 by 2. Similarly, if L is not the right child, okay, so we will ignore this value. If L is not the right child, if suppose L was here, okay, so we need to take this value, maybe this value or maybe somewhere else, because we want both of these nodes value. So without taking this node's value, we'll directly jump to its parent. Okay, so we'll say L equals L by 2, and same way, if R is left child, okay, we'll say it like this. In the reverse case, we will consider the value of R. We'll take the value of R. We'll make R go to different subtree, and if this is not the case, R will then point to its parent. Okay, and after that in the end, we'll just return the result. Okay, now what after this? Now we need to update it, but do we really need to update in this question? No, we are not updating it anyway. We are just creating the tree and then querying it. Okay, now what we need to do is, after it is done, we will iterate through all the elements. We will find L, that what is the minimum. Okay, or let it be A, that what is the minimum element in the range next the ngl of I and I minus 1. Okay, what I mean is, for every I, for where we wrote it, for every I we know that HL is NGL of I. So we need to find the minimum value in this range, NGL of I and I minus 1. And similarly, we need to find the value in this range, I plus 1 and NGR of I. Okay. So we will find B in the range I plus 1 to NGR of I, and then we'll simply print absolute value of A minus B, and we'll print next line character. Okay. Now let's try to run this code. Okay. Oh, we didn't initialize our segment tree. That is, we need to initialize it here. We need to create segment tree. We do segment tree st and we'll pass b here. Now we'll run it. Okay. For now, on the sample case, we are getting the answer correct. Submit it. Yeah, and this is how it was supposed to be done.